Good afternoon. My name is Ian Swasing from Percival Engineering. Today I'm going to talk about the Siemens S7 network protocol and how it can be used to interact with PLCs. Today I'm going to be providing an overview of the S7 network protocol. This will include its use cases, structure, and some of its most useful commands. I'll also be providing an overview of PLC memory. This will include the different types of PLC memory locations and the structure of a PLC's memory. To finish, I'll be providing an overview on issuing S7 commands using a client application based on the Snap7 Python library. The S7 network protocol is a connection-based, block-oriented protocol that facilitates communications between Siemens PLCs and other devices. These devices can include PCs or even other PLCs. S7 communications can be used for many things, including programming PLCs, exchanging data between multiple PLCs, accessing PLC data from SCADA systems, or PLC diagnostics and testing. See here for a very basic diagram depicting a single S7 connection over a network. At a high level, S7 is a protocol that can be used to issue commands from a client to a PLC server. Notice that for every request a client sends, a response is sent back from the PLC. This client can be an application running on a personal computer or even another PLC. Examining the different layers of the S7 protocol in the context of the OSI model, it exists primarily at the application, presentation, and session layers. At the transport layer, transportation is handled by TCP/IP using ISO on TCP to organize data that is sent. Looking closer at the transport layer of the S7 protocol, it's good to note that ISO on TCP, also sometimes referred to as RFC 1006, is used to packetize the TCP packet stream into blocks. It's important to note that base transport for this protocol still relies on TCP. Contained within the packetized stream mentioned a moment ago, the protocol data unit, or PDU, is the payload data that will ultimately get processed by the PLC. This will contain identifying information about the request. It'll have a command, parameters, and relevant data. We can now go a little bit deeper into the S7 PDU structure by examining a Wireshark capture for a request sent to establish a connection with a PLC. Note that there are several dissectors for S7 comms available for Wireshark right now. The one that I've used for this presentation was built into the current version of Wireshark I was using. First, you can examine the first diagram for a high-level view of the two S7 connection establishment requests. Notice that the ROSCTR field in the first packet is referred to as a job, or a command, and the second packet is an acknowledgement, or response to the original command. Note that the function field for both packets are the same, as both packets were involved in establishing a connection, setting up communications. Next, we can take a closer look at both packets. Note that most of their header characteristics are identical, including the protocol ID, redundancy identification, PDU reference, length, and data length. They also have identical parameter fields. A notable difference between the two packets is the ROSCTR field, which differentiates the packets between the request and the acknowledgement. Also notice that the acknowledgement packet's header has additional fields to account for any errors that are being returned to the client. If a request is sent and something goes wrong, the PLC will tell the client that something went wrong by populating these error fields. Now that we've described the S7 protocol structure, we can talk a little bit more about what the protocol can be used for. Generally, this protocol can be used to upload or retrieve information from a PLC. This might involve reading or writing different locations in the PLC's memory, establishing a connection, or retrieving the date and time. The PLC's memory is where data is stored that will drive how the PLC ultimately functions. This might include digital inputs, digital outputs, collections of data blocks, or even functions. As this data impacts the PLC system's functionality, updates to this data may correspond to an update in how the system functions. PLC memory locations can be thought of in terms of bytes, with each byte containing 8 individual bits. See the example diagram to the right and notice how the memory byte values may be represented in different bases, such as binary, decimal, sometimes even hexadecimal, but they ultimately refer to the same overall value. It's very important to note that individual bits can be very important in the context of the larger system. A change to a single bit in a memory location may correspond to significant changes across the entire system as a whole. Next, I will begin discussing the different memory types that exist inside of a PLC. These memory types can include data blocks, digital inputs, digital outputs, and marker bits. Over the next couple of slides, I will describe each of these memory types in detail. First, we can talk about data blocks. These can be characterized as function blocks, organization blocks, or raw data blocks. Function blocks are accessible across the PLC, and as the name implies, they will store PLC functions. PLC functions may reference data stored in other blocks, and they can even call other function blocks. Organization blocks serve as an interface between the operating system and the user program. They may contain the startup behavior of a PLC, and they might handle interrupt-driven or cyclic program execution. Raw data blocks are the simplest of the data block types, as they just store miscellaneous data, such as function parameters. These are accessible by PLC functions and are stored globally. Note in the diagram to the right that the organization scheme of this memory is the same as I discussed previously in terms of bytes, broken up into 8 bits. Next, I'll discuss digital inputs. As the name suggests, these store digital inputs to the PLC. Generally, these are driven by external inputs to the system. Sometimes this type of memory can be referred to as IPI memory. Digital output memory will store digital outputs from the PLC system. Unlike digital inputs, which are driven by external factors, this will be driven by the PLC's programmed logic. While it's commonly referred to digital output memory, it may also be referred to sometimes as IPU memory. Marker bits are a little bit different than the previous 3 memory types I've described. They're commonly used as flags, indicators, or statuses, and are often referenced 1 bit at a time as opposed to as bytes. Sometimes marker bits are used to control program flow, and sometimes they're also used to hold temporary data. As a piece of trivia, the term marker is actually German for the word marker. Now that we've covered the structure of PLC memory and the S7 protocol, it's time for the big question. How can we implement S7? Our solution will need to be able to keep track of a connection to the PLC and responses to any requests we may send. Now to introduce Snap 7. This is an open source library that's available to be used both for C++ and Python applications that can interface natively with Siemens PLCs using the S7 network protocol. It's important to note that this is a library that was originally created using C++, and it is only possible to use it for a Python library using C types. It's also important to note if this library is to be used for a Python application, it will need to be pip installed using the command below. So, why is Snap 7 so useful? The first useful feature Snap 7 offers is clearly defined functionality and well-named functions. This makes it fairly easy to use Snap 7 to perform S7 operations on different memory locations of a PLC. In addition, packet creation is abstracted away, which will save a lot of time. It is much easier to use Snap 7 to send commands than it is to manually create S7 packets yourself. In addition, synchronous functions will wait for a command's response before returning. Finally, large commands sent with Snap 7 are handled gracefully and don't require any extra logic to manage. Now that we've covered Snap 7, I can introduce the CTF Python command line interface. Developed by Percival Engineering for use during this Capture the Flag competition, this is a Snap 7 based Python client that is wrapped in a user-friendly command line interface that was built using the Command2 Python library. This application will manage connection logic between a client and the PLC server. It will also provide commands that will be able to interact with a PLC over a network. Note that this application will use Snap 7's implementation of the S7 network protocol. Copies of the CLI client will be provided to CTF participants on the day of the CTF. Examples on how to issue commands from this application will be provided today during this presentation. Some examples of S7 commands that can be sent from the Capture the Flag client include obtaining the date and time from a PLC, reading and writing from data block memory, reading from digital input memory, reading and writing from digital output memory, and reading and writing from Merker bytes memory. In a moment, I'll open up a terminal and demonstrate some of these commands from the CTF CLI. Before demonstrating how to use the CLI application, I'd like to go into how to start the CLI. In the first image, I've run the CLI program with the TAC-H or help option. Notice that the positional arguments include the IP address and a port for the PLC you'd like to connect to. It's important to note that if the IP address or port of the PLC you're connecting to are wrong, the application will not start and an error message will be printed. See the second image for an example on starting the CLI successfully. In the demonstration portion of the presentation, I'm going to show you how to use the CTF CLI you'll be provided during the competition. To start, I'm going to show you how to begin the application by entering in a valid IP address and port that will correspond to a PLC on the network. However, first, I'll show you what happens when you provide an invalid IP address that does not correspond to a PLC on the network. In this case, you'll get the error message of an unreachable peer, and the application will not start. Similarly, with an invalid port, in this case 106, you will get a connection refused error, and again, the application will not start. So it's very important to get the IP address and port values correct for everything to work as expected. Once the CLI is started up, the first thing you'll want to do is use the help command to list all of the available commands that can be used. As you can see, we have several commands available that will be used to read and write to Merker memory and to interact with data blocks on the PLC. To begin, first we're going to read a specific value, a specific Merker bit value. We'll read the first byte and the third bit. So as you can see, the third bit of the first byte, Merker byte, has a value of 0. So next, what we're going to do is we're going to write that value using the write mbit command. As it is currently a 0, we are going to update it to a 1. Notice that the first parameter corresponds to the byte value, and the second parameter provided corresponds to the actual bit being referenced. For write operations, the third value is going to represent the value you're going to be changing the mbit to. So, we've just written the byte, or the bit. So repeating the first read operation, we can see that the targeted bit has been updated to a 1 value now. So now we're going to repeat the same process, but with a Merker byte. In this case, I'm going to read the 7th Merker byte. Note that in this case, you do not need to provide a bit value, as the entire byte is being referenced. In this case, the Merker byte's value is 0. So we are going to update that value to 253. Once again, we only need to reference the byte value as we're updating the entire byte. Checking to make sure the command has gone through successfully, we read the 7th byte again and can see that the value has been updated to 253. So I'm going to show you what happens when a command is given invalid parameters. So here we're going to try to read that same byte, but now we're going to give it an extra unnecessary parameter, in this case an 8. So when something like that happens, you will get an incorrect number of arguments error, and it will show the correct format of the error, or the correct format of the command in question. If you're interested in seeing a little bit more detailed information on a command, you also can use the help command followed by the command to get a little bit more information. In this case, it just tells you that this command is used to read a Merkle byte and gives you an example format. That will give kind of a hint as to the expected parameters. So moving on to the next commands, we're going to read a Merkle word, which is a collection of bytes. In this case, we're going to read the 14th word, which has a value of 0. So similarly to the last couple of examples, we're going to now update this word. We're going to give it a value of 1,000. Now to check to see if the command has gone through successfully, we can see that the 14th Merkle word has been updated with a value of 1,000. Now we're going to transition into the block commands we've provided here. To start, we're going to use the list blocks command to see how many of each kind of data block is available on the current connected PLC. It's worth remembering that there are several different types of data blocks available, including function blocks, organization blocks, and just raw data blocks. In our case here, for instance, we can see that we do have a function block and several raw data blocks available. So next, we're going to get block info. However, this is an excellent time to reaffirm that you can check the parameters to a command with the help command. So here you can see that we're expected to provide a block number as well as a categorization of block, in this case splitting between organizational blocks, function blocks, and data blocks. I'm interested in the function blocks for this example. So we're just going to give it the function block category. And we'll give it a block number of 0. So as you can see, an error is thrown here because the block, the function block that's available does not actually have a block number of 0. It has a block value of 1. So yes, when you execute these commands, if a block you're trying to obtain does not exist, you will get an error and you'll need to adjust your parameters and rerun the command. So the get block info command, as you can see here, provides a collection of information about the block you've targeted. Moving on. We've been able to read block information. Now we're going to start manipulating blocks using this CLI client. So to begin, we're going to start with the block upload functionality. The naming is a little bit counterintuitive, but in this case, what this command does is inform the PLC to upload information from a data block back to our client. We're going to copy information from the function block we targeted earlier, which has a designation of FB and a block number of 1. This local file name can be any file of your choosing. Before you run this command, you will have to create this file. The command will not create a file for you. In this case, I have just created a temporary file here, /temp. And that text file I created has been filled with 158 bytes that belong to the data block we've targeted. Now onto the final command. As we've just uploaded the block, we can now download the block, which, again, a little counterintuitive. In this case, this download command will actually inform the PLC it will be downloading information from our client. So in other words, we'll effectively be sending data block data to the PLC with this command. Okay, so once again, we'll be giving it a block type of FB, or a function block. We're going to give it a new block number of 2. And once again, we're going to reference that local file. This will work as this file already contains information on a function data block from the previous command we executed. Okay, excellent. So now that this command's finished, all of our data that is contained in that temporary text file has been written to the PLC. So we should be able to once again list blocks, which will list all the data blocks on the system. And we can see that the field for FB, or function blocks, has now gone from 1 to 2 blocks. We've effectively added a new function block. And it is worth mentioning that the contents of the function block you add can be pretty much anything as long as you store it in a file. So you certainly could go through and modify it if you need, or obtain different data for a data block rather than just copying one. This will conclude our presentation today on the Siemens S7 network protocol. Thank you so much for watching. Please let us know if you have any questions. Thank you.